All right. So um, like we did before, we're gonna just briefly go through the questions that is in exercise 3, uh, and the way. And so we're gonna mainly talk about the theory question, and also if there's something wrong with that you need to want to discuss with the code implementation, that is also possible. So feel free to just ask when we share your opinion or ask your doubts for when you have when you have something to say. So let's get started. Let me share my screen. So let me know if you guys can see my screen.
Yes, I can see your screen.
Okay, great. All right. Okay, so the exercise session 3 is about supervised learning and the large scale problem. So that's may corresponding to basically kernel PCA and then large scale problems that responds to the like fixed size SVM. And so for this one, so first one is a kernel PCA, and then you basically, so for this exercise, the 1.1, so you basically need to run this script here, and then you need to describe. So this, let me check code. It's fixed size. So basically, this is a bunch of you are having this script, which is like you need to decide the number of the data points and also the dispersion of the data set. And then you need to use the kernel PCE to kind of like let me check again. So you need to use compare the linear PCA and the kernel PCA performance, and then you basically change. Like I said, you can also, there are some parameters that which you need to choose during when you're running the script. So you can run the number of you can change the number of the principal components, and then you need to compare the difference between the performance with linear PCA and kernel PCA, and then in the end you are trying to ask to kind of like provide a strategy or kind of like idea about tuning the number of the components, and then the hyperparameters and the kernel parameters. So I kind of I'm just gonna directly jump to my report and just give you an idea what does this result looks like from what I get. So are you able to see the plot clearly?
Yes, I can see.
Your voice is very low. I didn't hear. Hello?
Can you hear me? Hello.
Yeah, I can hear you, but it's really like your voice is very low.
There's something wrong with my microphone.
Okay, now it's getting better.
Yeah, okay.
Okay, so are you, so you guys can see the plot, right?
Yeah, we can see.
Okay, so basically what I did here, so first plot is like the input data is a visualization of the input data, so you get something like this. So this one you can just like get this by, you know, like when you, if you put the, when you ask you to put the data set dispersion, so if you just put the 0 here, so it's like just original the input data, so there's no noise, so you will get something So basically, get something like this. So this is like more or less like the nature inside the nature of this data set. And then, of course, then when you're doing your like kernel PCA or linear PCA, you will need to add some of the noise. So I just use the default setting. So this is basically the one next to it is like the result of a linear PCA. So basically, you are just getting a line here for getting, which is like the principal direction of the maximum variance. So and then you start to experiment with kernel PCA by changing the number of the principal components. So then I start with 3 and 6 and 12 and 24. So this is like basically generally the result. Okay. So and then you need to basically describe how did you do denosing with PCA and describe what happens with different if you increase the number of the principal component, basically. Okay, so for discussing how did you do the denosing using PCA, so I think if you check the slide for this course, for this part, so it's lecture 9, and then I think somewhere, so in this, so it's here is already kind of like discussed, like how did you denosing with kernel PCA. So basically, I think you can just I think a person probably needs to discuss what its kernel PCA is doing, and then when you're trying to denosing, what kind of like formula that you're trying to, because in the end it's optimization problem. So you need to, I think you need to mention this kind of like what kind of a formula you are trying to minimize. And then after that, yeah, that is just example. So I think this is, so you discuss what is PCA, and then you discuss what they are trying to minimize during the denosing. And of course, then you discuss, okay, when you increase, when you are doing with kernel PCA and you are increasing the principal component, the results you are getting. So you see that if you increase more, so actually the principal increase more the number of the component, actually your result is actually kind of like how do you say? I kind of describe it like overfitting, because it's trying to overfit every like noise point you have here instead of like catching the, like, how do you say, the main characters. So because that's why you need to kind of like optimize tuning which one, like the principal component, number of the principal component is best suitable for your kernel PC. All right. So any comments on the first question? About this?
Nope, I think it's clear.
Yeah, so this is it is pretty straightforward, I would say. It's just something you need to run and observe. And then the second question is basically very theoretic. So you need to basically discuss the difference between linear PCA and kernel PCA, and how many principal components can you obtain, okay, for both, I guess. So for that one, well, again, I suggest you again just go through this note, this lecture content, and then try to so you try to grab some of the concept and some of the formula here. So you need to discuss what is of course what is, when you are doing linear PSA, what kind of formula you are trying to optimize. And also, of course, you need to mention that the kernel PCA is like brings the input data to can bring input data to a higher dimension by using the feature mapping. So let me check which slide is this. So yeah, so basically you are creating a nonlinear version of method by mapping input spaces to high dimensional feature spaces, and then you apply the kernel trick. And this is the optimization problem in the primary form. And then yes, so and then I think that's basically you need to say about what is basically those two PCA we're doing. And for another one, so you need to compare how many principal components can you obtain here for both two. So for linear PCA, I think the maximum number of the the principal component you can get is the number of the input, number of the if I remember correctly, it should be the number of the data points or the input dimension. I think it's the input dimension, right? It's I kind of, because we are doing this
Yeah, it could be dimensions.
Yeah, it's a maximum number of the is the input dimension, right? Okay. All right, and so basically, but for kernel PCA, then because you can actually, so let me check which slide is talking about this. So here, so the nonlinear PCA, like you basically first they transfer your input data into high dimensional, and you can, and then actually depending on your kernel, the choice of your kernel, you can be infinite if you want. So but then you can the number of the score variable you can obtain. So basically you are getting I would call it like NS new dimensional space, and it can larger than your input of it can be larger than the dimension of your input space. And so then of course your possibility of the principal component can be, just between 0 and NS. So but NS is something I think is depending on your choice of your kernel, if I remember. So basically, yeah, that's the difference, like how many number of the principal components that you can get for both PCA. So is that any comments on this one? This question? If there's nothing, if you guys think it's okay, we can move on in 10 seconds for the next one. All right, so let's move on to the next one. So the end, so you need to propose a technique to tune the number of the components. So basically those parameters, okay? Let me check. So if you record this digit, if you record this script, so I think the owning, so this again is it's kind of like similar to what we have with reconstruction of the PCA. So basically what you need to do is like you need to fix the number of the components, and then you use auto parameter tuning or grid search to find basically the hyperparameters and the kernel for the kernel parameters and the hyperparameters. And then you calculate for each, basically for each number of the components, you start to calculate you compare the reconstruct like the arrow between the original data and then the one you obtain, and then you just choosing the best, like tuning the parameters by which combination of the parameters actually minimize the reconstruction error. So check what is that right. Yeah. So you first fix the number of the components, and then you try to optimize for each number of the components. You try to optimize those things, and then you try to calculate the reconstruction error, and then you just use the one with the lowest reconstruction error. All right. So that's my ID. So any others want to comment on this, or they have something different?
I could add that there seems to be the necessity to do an epsilon tube, like a range of reconstruction error, which is desired when you're denoising the data, because you only have the data with noise and you want to bring it back to denoise data, right? So there has to be a range of change in your reconstruction that you want to allow. So I also put that, like something really similar to what you had, but I also thought that was like that was important.
Yeah. So just use this plot as an example. Okay. So this is your, let's say this is your input data, and then this is your, I don't know how many points actually we are getting those things actually. So basically you are, once you are done with your PCA, and then with your PCA, and then you just compare those. You just compare like the data you are getting from here, and then compare what is the difference between those two. And then you based on that, you can calculate the how do you say, the arrows. Okay. So I think we are talking about pretty much the same stuff, I guess. Not sure. Anyway, any others wants to has more feedback or a question on this part? Okay, if not, we're gonna move on. So this one is second one is talked about the spectral clustering. So I was actually kind of surprised that we are kind of getting this kind of question, because this one is actually belongs to the last lecture, which professor says he will not ask during the exam. So I'm not sure why we are doing these exercises. But if he gonna ask some question about this part, I'm just saying I listened to your advice and I didn't study anything about it. But anyway. All right. So for this one, so first we need to explain how this works. Well, I think you can, first of all, you can find a number of the, if you just search what is spectral clustering, and then you will already find a lot of the materials in the Google. And also maybe, and then maybe you want to go to that last lecture and just listen to the part of this spectrum clustering. So there are two resources. And then you just describe whatever the way you described. So during the like exercise session, so actually one of the TAs sent us kind of like her hint about this, like how do you say? He sent us some kind of like materials, which is like the question which has been asked before, and here he specifically talked about this kernel spectral clustering, and she trying to basically describe like, okay, you maybe need to refer to this. So maybe, I don't know, it's a good idea just to put it somewhere. Like, I don't know if I can just put this and put it somewhere in the page like that. Like that. Don't have the pictures. But anyway, so maybe later I can create a page maybe about this, like it's about, I don't know why there's no pictures, but then I can put the page here and later on you guys can just review it. So I think I don't so I don't really feel like to explain how this works, because currently if you just search it on YouTube or Google, there are a lot of information already. So and then you have I'm just gonna point out those sources that you can use to answer this question. Do you think is that okay?
Yeah, that would be good.
Mm-hmm. All right, and then you need to tell the difference between what is spectral clustering and what is classification. So again, you need to kind of like write about what is the essentially what those two are doing. So maybe put some of the formula and then also how the spectral clustering works, which you described before. So there's one of the screens. So basically, there's someone is a noise from someone. Okay. So I think for this materials, you probably need to refer the last lectures, the slide of the last lecture. Let me check. And then you probably gonna be, yeah, you probably want to start from trying to use these materials and maybe like here. So this, I think this formula is quite important. One of the, so basically describing what you are trying to do. And then this is the formula, like the primer problem for this spectral clustering. So if you remember from previous slide, then actually if it comes to the classification, you are also trying to actually minimize one of the function looking like this. So I think maybe it's a good idea to mention that as well. So you're just telling, okay, look, you are basically trying to minimize two different so this one is the one I just copied from the kernel spectrum cluster, and this is the one which is like the LS-SVM when it comes to the classification problem. So I think, yeah, I think you mentioning those two should be okay, but I don't know if there's other people's opinion on this, like other points that you want to mention as well for this problem, for this question.
Well, I think the key point is that the spectral clustering doesn't have any labels. So you are trying to find two different clusters and you assign labels to each data point. While to the contrary, the classification, you already have all the labels and you're trying to build a model to classify them correctly.
Yeah, so they were right, because actually I mentioned that the spectrum clustering is supervised learning and classification is supervised learning. Yeah, that should be the first thing that you should mention, I guess. They are basically two different type of learning. So, and then you start with this kind of like formula details. All right. Yeah, I forget to mention that. Anything else? If not, we're gonna start to discuss go to the next one. So again, the next one is you are just asked to using that script, and you are trying to different value of sigma 2. And then you need to discuss what is the influence of this sigma 2 on the clustering result. So this is basically the result I get. So basically you are getting those kind of like data sets of like two rings, which are kind of like containing each other. And then you see that, well, if you're just trying the values that they recommend here from like 0, like 10 to the power of the -3 until this. So you will probably get something looks like this. Okay, so you are keep increasing the sigma 2. So actually you see that actually in the first one, if it's very small, you are actually not able to label those two like rings basically. And then you start increasing the value, and then you pretty much get the same until this one. So those from here to here, you are able to how do you say, the cluster those two rings correctly. But then if you increase until this, and you see that then it's kind of like for this part, which is the for the data point, which is like in this close to the other ring in the center of this part, they actually becomes you classify as another cluster. So then it's not what you have in the previous tree, basically. Okay. So again, so what is the influence of sigma 2? So you might want to record that in the previous exercise, sigma 2 is actually it's kind of like represents like the influence for each data point. And then the bigger the sigma 2, then the more influence for each, like the range, influence range of each data points. So in the beginning, because it's really small, this is so okay. So this is just pure my opinion. Okay, just not just for the record. So when it's like really everything is very small, so even like these data points, they are really close. Even though you looks like here they are very close to each other, but then because this schema 2 is too small, so they are just like every point belongs to their own cluster, so it's not able to actually to group or merge with other data points. And when you start to increase it a little bit like larger, and then you are able to see, okay, those points they merge with the one which is next to it, and they start to doing this, and then you get this kind of ring shape. And if you keep increasing, that's okay. But then when you get this 0.05, so then actually the points, let me zoom more on this. So let me jump into the next. So when you are getting like here, so if you are keep increasing, actually you see that like the points you consider that the points from here is actually also like they are considering, even though they have this distance, then it's kind of far away, but then they are still considered as one cluster. So if you keep increasing, even though then you should expect this could happen, even they are far away from here. But I think this, if you increase to this kind of scale, it's not that. I don't know what is the distance from the center from here to here. And then it's just like, if you're, because each point, the influence of each point is much getting bigger, so you will accept then, like, if the sigma 2 is like really large, I think then every like data points here again will become one cluster, I guess. I haven't tried that yet, but I would expect that. So that's my comment. So any others wants to comment on this one?
Can you hear me?
Yes.
Hello. When I sent sigma equal to 0, 0, 1, just like the second picture of the screen. Your picture is green, but in my code, I I can separate these two rings. I don't know why.
Actually, I had this error before, and I just run it again, and I got the exact same pure blue as this one. So it's weird. I think you can just run a new trial.
Do you mean I'm wrong if I use a sigma equal to 0, 0, 1, I get I separate two rings?
No, I think it's the script. So I tried just a few seconds ago, and the first time I typed 0.001, the results was 2 rings separated. So one yellow and one purple. And I run it again, and I got the exact answer as shown here. So yeah, maybe you should try it a few times. I didn't change anything, so I think there's something wrong in the script, maybe.
Yes, but I think there is no exact time about whether the sigma equal to 0, 0, 1 there should be separate or not separate. I think maybe maybe I got the separate rings is right or not.
Okay, so any others is getting different results for the sigma 2 equals this 0.001?
Yeah, I also get the rings separated with 0.001.
Okay, let's just run it right now.
I think maybe it's right.
Yeah, same for me. It depends on when I run it. Sometimes it's separate, sometimes it's not.
Okay. Let me check that. This one, right? So 0.1. And let me just run this. Oops, I think I didn't add the pass. Okay, run it again. Wait a minute. Okay, I need to run from this directly. What? Threshold function.
On your line 33, there's a W. You should remove it.
Oh yeah. I think I just type it. Oh, okay.
You can
So this-
separate it.
Yeah, you can separate it now.
Yeah.
Can you try to run it some other time? Because why do a second time I got unseparated?
Oh wait, I need to press any key in sequence. Sorry. Let me just. Okay, now let's run it second time. Ah. Okay. Okay, then
I think both
something.
of these results is right.
Yeah, let's just run it to just make sure, keep running. Yeah, so again, so you get something like this now. So I think,
To me, I have to get this right, this result, not
No,
separate.
actually,
Not
I,
really.
I don't think so.
Yes, yeah.
Maybe can you try to make segment 2 even smaller, and we
yeah,
can see.
yeah, that's, I think that's gonna happen, because now I think there's a probability that if it's not so small enough. So let me check if I add one more zero. Oh, okay.
Yeah, it's not separate.
But this one is wrongly. Okay. Yeah, I didn't notice this. Okay, let me just try to run this one again. But this is entirely wrong already. Okay. So let me try something like 0.5. Okay. Yeah, now this is okay. So then I think actually my result is actually an unpopular one, I would say. Or if, I mean, if the sigma 2 is 0.1, like this one, 0.001. So let me just try again.
It's separate. You can separate it.
Yeah. So I think I make my conclusion too early. Okay.
I think both of these results is right. Maybe sometimes it's a have probability to get separate or the same.
Okay, so let me.
Do you agree? Do you agree?
I'm not sure. I'm not sure what is happening here. So I think yeah.
I think probably it's the scripts problem, because when you look at the matrix, the sorted eigenvalue matrix, so for the unseparated solution, that is the same as unsorted one. So basically, the whole script did nothing. I think it's the scripts problem. If you can like reproduce the plot.
Yeah. Let me try. Give me some luck. Nope. Try the. Okay, so now I get this again. So which part you are saying that like this?
And you can type a key because the next plot would be the matrix. And there should be
Matrix.
another one. Yeah.
Can you show your
So
kernel matrix?
normally after the algorithm, the right plot should be sorted one, but you can see there isn't any sorting. So it looks like the algorithm did nothing, right?
Yes.
Okay.
Yes.
Yeah, it's indeed. Yeah, I think they are identical.
When the sigma equal to 0, 0, 1, I get the separate terrains and the kernel matrix. It's
there should be like
different.
two squares separated in the. Yeah, that's the exact like why they got two clusters. So basically, you sorted the eigenvalue matrix, and then you run the k-means algorithm. You can obtain two clusters, and that's the way I understand it. So from this port, I think the algorithm didn't run at all. So maybe it's the script's problem. So.
Okay.
Yes, I have another question. When I get the 0, sent the sigma to 0, 0, 1, I found my kernel matrix. The weight point is very weak. It's very weak. It's seem not too strong to separate in my kernel matrix. The white points, the white points region just like very weak.
Okay. So I think for this one we can because we still need to discuss other issues. So for this one, I think I note this down, and I probably after this our call, I will kind of like write a like email to one of the TA and ask them why, like, some just to see if we can get some answer from them. So then, of course, then what I described before, it's then it's starting to make too much sense now. So what is the influence? Well, if that is the case, actually, yeah, if you just I think it's still, I think for sigma 2, so you still need the sigma 2 be like in a good range. You cannot be like too small or too big so that you can get to the correct like desired cluster results, basically. So that is but for the influence, we need to, yeah, kind of like I think we can still using the same ID which we use which you use to answer the previous answers. But then yeah, I would just check, like send the email to TA and say what else, what is their suggestion on this one. But if you guys have any ideas also trying to like a reasoning about this, you can share it now if you want.
Well, what I wrote down was basically based on the kernel matrix and the projections on the subspace. So if you don't tune the sigma 2 correctly, you don't get really tight results from the kernel matrix. And if the sigma is totally off, the results you obtain would not be two separable squares, and there would be other noises. And those noises correspond to when you do the mapping on the second and the third eigenvectors, the two rings would not be mapped to two different clusters. So if you look at the third plot you get, normally the purple one and the yellow one would be nicely separated with enough space between them. But if you have noise, then the results would be just different. And that's the way that's the way I write.
Yes, so I think, yeah, I think then this part again goes to here. Like if you,
Yeah. So basically, what I understand is that how many clusters is dependent on how many separable squares you can find from the sorted matrix. And if there are some points cannot be sorted into a square, then those would be resulted in like unseparated clusters. So, and the sigma 2 plays a role in how you get the Laplacian matrix and the resulting k-means algorithm.
yeah. Okay. Let me just quickly check the figures which I did before about those matrix. So this one, yeah, so this is one I get like the one with the unseparated one. Like then it's just identical after sorting, after this sorting. And then this one is 0.01. So then one you can see those two clusters like very easily and separate like into two regions. And then let's check, this one is 0.02. So this one it's yeah, very separated. And then here also 0.05. And here, yeah, so here is like the one which has like wrong cluster. And so you see that there are some noise here, like between, instead of like purely blank. So if you see something like this, then you will anticipate that, how do you say? Then you will anticipate it will not be a very good clustering result. Origin, let me just check. I think like with the more sigma 2, you are actually getting more noise, right? So if you, I think like you just, because this one, you compare this and then you compare the image you get here. So this one is less noisy, I would say. And then this one is, yeah, this one is too small. Yeah. So if you are adding, so the effect of this sigma is basically adding noise to the kernel matrix in the original data, I guess. All right. Yeah, I think that's a good point. Just you discuss like the sigma 2 between the so the effects on this kernel matrix. All right. Okay. So yeah. So that's fair, I would say. Anyone else want to comment on this? If not, we're gonna move to the next one in 10 seconds. All right, so now let's move on to the fixed size LS-SVM. So basically, from what I understood for this one, you basically it's the context is like what do you do with large data sets with a larger amount of data points, and then you are basically trying to so you don't want to use all the data points to compute, and then you are trying to how do you say, find some representation, like you're using much less data points to actually represent the SVM model, and then basically it's like this how do you call menstrual? I don't know how to pronounce this correctly. So it's trying to basically find some like represented points to actually to represent the whole, like the very big large data, like the characteristic of your big large data set. Okay. And so it's again just running some script. So the first question is like very theoretical one. So when do you want to solve the problem in the prime or in the doom? Which one? Like you need to discuss which one. And then so if you then it's actually very clearly discussed in the lecture, and also in the lecture slide as well. So basically the idea is that if you have let's see, this one, right? Large scale problem, yeah. So I think this plot kind of answer what do you should do. So if you are having a large number of data sets, and then you have, but this data, it's actually not so large, have a high dimensional. So then you prefer to do it in the primary space. And if your data is like having a high dimensional of the input, and then you should prefer to do it, and it has like not too much data points, then you should do it in the do space. Solve the computation in the do place, basically. So that's the answer. But then of course you need to maybe add up something to explain why you think like that. So I think for this one, if you guys want to mention, I think check where do you find this. Check it. Oh. Let me. So I think for the first one, so why do you prefer to do it in the primary? Like this is for solving the data with just large scale amount of data. So I think there's somewhere like the slide mentioned about it. Let me check where is it. Okay. Well, I think I kind of like I was trying to read the textbook about this part. So I think in the beginning of that textbook part, they have been like a good extent. They introduced this why you should do it like when you have large number of data, you should do it in the prior space. And for the second one,
I think it's just this formula. I use this formula. So basically, when you have a large number of data, in the primal space, you are only interested in this W vector, which is related to the number of dimensions you have. So if the data set is large, but you have like only 2 or 3 dimensions, solving the primal optimization problem only like takes less time to find those 2 parameters. Yeah.
And I think I remember if you choose to do it like in the do place for this one, again, when you have a bunch of data, and you actually need to compute like the alpha, right? Like this alpha.
Yes.
And then this alpha is like the number of the data points, which is huge. So then you don't want to actually. It's more computation if you do it in the do place. Yeah, I remember that one. Okay. So again, so when you do it in a do place, because when the computation is actually related to the dimension of your input, so that's why you want to do it in a do place with kernel, because that is then your computation is actually independent of the dimension of the input. So it's just based on the choice, and then based on the choice of your kernel. And also because you have like not so much data points, so like I said, the number of the alpha you need to compute is also very small. So then you want to prefer that this large dimensional input in the do place. Okay. I think that's that's good. I mean, thanks for adding this to this question. So I think we can move on. So what is the effect of choosing the sigma 2 on the fixed size on the resulting fixed size of data points? And then can you intuitively describe what the subset? Can you describe to what subset the algorithm converge? So you just need to change the number of the sigma 2 here, and then so I think I get something looks like this. So actually the original data, like the original number of the data is actually kind of like Gaussian, like a standard distribution. So so if you look at this blue point, it's like a standard distribution with a sigma of with a mu like in 2 or something, 0 or 2. Yeah, I think it's 0 with a center of 0 and sigma equals to 1, I guess. And then you are choosing this point to kind of like represent, trying to represent this kind of like the whole data set, basically. So as you can see, that the more sigma you have, then the more like the number become like those sub data sets. It's actually more. So if it's really big, small, and they are actually more close to each other, and then if you have like a big one, like 210 or 100, then you will get like them. They are like really not exactly. Like not really so close to the Gaussian, like the standard distribution before. So I was just saying, okay, yeah, again, you need to carefully choose the sigma, these parameters, and then of course I think I mean based on this, what like it's asking like what this subset should be like, basically. So I mean, so if you choose, I just saying, okay, if you choose the right sigma 2, like the suitable one, then it's actually trying to represent this kind of like a normal distribution that you you start with. So let me check the code for this. So let's fix that script. Which script is using? Fixed-size script 1. Okay. Yeah. So this sigma 2 is actually in this in the RBF kernel. I think it's one of the parameters of the RBF kernel. Okay. So yeah, so basically that's what I think about this question. Any comments on this?
No, actually, I don't really understand what the question tries to ask. And I thought it's trying to ask like what kinds of data sets, if you run this algorithm, the result would convert. And I think the kinds of data sets there should be some Gaussian patterns. Otherwise, if it's just random noise, then the algorithm wouldn't find any meaningful data point. That was my answer, but I'm not sure.
But did you get to something similar like this data points, like when you're increasing the sigma 2?
Yeah. I didn't use 100. That was too large. I used 5, and to be honest, the difference wasn't that much. But I described that with an increasing sigma 2, the peaked points started to moving from the inner to the edge. So it's kind of a similar things you just described.
Yeah, I think so. Okay, but yeah, I mean, I don't know whether it's something. So, but the incision, yeah, I mean, from what we understand about fixed-size SVM, then like from this, so you are using this kind of a representation, like to basically use a smaller like the subset of the data of the large data set, trying to and then you use those data points actually to like as a kind of like a representative and also as a kind of like a approximation. So you should I think you should expect that those kind of like a representation should already like having a lot of characteristic of the original like the data. Okay, so if you take a look at the slide from the lectures, so they are talking about some of the example, right? Check where is it? So I think yeah. So for example, you're getting a lot of data sets like 20,000 for this sync function like regression. But then what you did with this fixed-size SVM, that then you just choose like how many points, like 10 points from those two, from this original data set. And it's, yeah, you can tell it's kind of like representing a lot of the characteristic of you get like 10 support vectors for this, basically.
I have a question.
Yeah.
Can you hear me?
Yes.
I think when the sigma sigma square is increasing, I find I think I can show my answer. Wait. This is my answer. Large value of sigma square seem to result in a selection that is more evenly spaced, which makes sense because it finally converges to the maximum the quadratic Rye atropine of the subset. I didn't use the large value just like you, yeah, sigma equal to 100. my biggest sigma value is equal to 5, and I can see this range point just sprint evenly. So I think this range point can represent the whole data space. So I think it's converged to the maximum value of the quadratic array entropy. So that's my answer. But I find when the sigma value is equal to 100, I think this red point cannot represent the whole data space. I don't know whether my answer is right or not. That's my question.
I think it's right. Based on my understanding, the sigma 2 value determines like, just like what he said before, like what we previously discussed, a small sigma 2 value focuses on more like individual data points. So when the sigma 2 is really small, each individual data point plays an important role in this whole data set. So when you do the selection procedure, there isn't much like advantages to pick outside data points. But if you make segment 2 larger, till the point that because our data point, it's a Gaussian distribution with its own sigma. So when your sigma is close to that sigma, then the picking point would converge to like the representative point. That's my understanding. And if you pick sigma to too large, then the algorithm would assume like your data set has a really large variance. So it tends to even look at large variance points, and those appear in the edges. So yeah, I think this could answer why with increasing sigma 2, those points and in your distribution seems to be like evenly distributed, because in that case, your selected sigma 2 is close to the real variance of this Gaussian distribution. So the point they pick based on the reigning entropy become more representative.
Yes, but but you can see this green when the sigma equal to 100 and this red point cannot represent the whole database. Maybe I think there's nothing related to the quadratic array entropy. So maybe it's a particular case in our experiment.
Okay, so can I just recap what it has been discussed? So you are discussing from here, right? I think, are you, so you are, because from this, so I think this part of code is using this quadratic reigning entropy, right? So basically, you are just first, you start with some bunch of, you start with some kind of like a subset of M support vectors, and then you randomly select one, and then you trying to calculate, okay, if you could, if you get this one, and then you're trying to place the one in the training set, and then you basically compare, okay, if you do this kind of a modification, then you calculate the entropy of the subset, like new subset. So if the new, like if this entropy is like, how do you say, is lower, or if the entropy increase, and so, and then you will kind of like accept it, this new data set, and then like you accept this as a new subclass vector, but then if it's not increasing, then you just reject it and just do it again. Just try to select it again. And then what else you do? Calculate the kind of for the present data set quality entropy equals to. So this is, I think this is what this thing they are saying is converge to, right? So in the end, your subset will converge to this kind of entropy. Did I understood correctly? From okay. Yeah. So this is just to answer the last one, but then we discuss about the sigma 2, the sigma square. So it's like so you more increase, you are tending to select the point which is more far. Like when you do the section, you are tend to select something which is far from the I don't know, how do you say, like the previous data sets.
Well, I don't really know how to explain like why a big sigma 2 resulted in like more edges points being selected, but intuitively a small sigma 2 means each single data point is important, so you don't have any preference choosing the outside one, and that's why you have many inside data points. So that's my understanding. And I think it's because in the RBF kernel, you have sigma 2 in the denominator of the exponents. So with a big sigma 2, then everything like that e to the power something becomes just 0. So that might be the answer. I'm not sure, because in that case, you don't have any influence for the RBF kernel. Yeah.
I have something similar written, in the sense that a big sigma, normally RBF kernels with big sigma are able to describe the general shape of the data with only a couple of support vectors. Like they usually have a sparse solution, because they're able with just a couple of points to get the general shape of the data, but the most of the details are lost. So they won't be able to replicate the detail within the data, but they will be able to get the general shape. So we should expect the really low sigma squared to capture most of the detail that occurs within the I would say the first principal component, like the component that has the most variance, and we should expect the larger sigma squared to be able to replicate the general shape of the data, and for that it needs points at the edges. I'm not sure if I explained myself correctly, but it's kind of in line in what you were saying.
Yeah, I think intuitively, if you can explain what you observe, it would be fine.
Okay.
I think that details of this large scale data problem is not important because we want to use this limited support vector to get the general shape of this large scale data space.
All right. Okay, so yeah, I think we have heard some good ideas about this. So just to conclude, briefly conclude what you guys just discussed. So for sigma 2, so if you have a like small sigma 2, so your supportive, like the subset you choose is actually more like they're more trying to describe like the details or a small part of the data sets. But if you keep increasing, they will try to, like they will trying to discuss more region, like the region of this large data set. And if you keep increasing, then actually they just describe they just go to the like how do you say, the edges or the boundaries of the data sets, instead of like they tend to go somewhere, you know, like which is less with like the boundary of this distribution of the original data set. I was okay. All right, so let's move on. So it already has been 1 hour 20 minutes already. So let's move on. If you still have any questions, so you can always interrupt later on. And again, okay, so now comes to I would say comes to the part you are like, so I think this is next question. So which will come later will become the homework question also. So you just run this script and then use this Wisconsin breast cancer dataset, and they just run it with fixed-size LS-SVM and this L1 approximation in terms of the and then you need to discuss the performance, which is like the result, which has like test errors, number of the supporter vectors, and the computation time. So everything is like you just need to run the script, and you just need to change whatever the data set that you are asked to doing. You are asked to use. Let me check here. So yeah, so you just basically use this script and just run it. Well, during the running, I didn't actually change. I use all the default setting of this code, and basically this is what I get from using the Wisconsin this data set. So I don't know if you can see the plot clearly though. So we just compare those results between those two. So FS LSVM and also this SVL L0 norm in terms of this three kind of like perspective. Okay. So you see that this arrow, I don't know if is there anyone is getting like the similar result here?
Yeah, my results look really similar.
Okay. So at least we can make sure this is everybody's results.
I got a different results. Sorry, I got a different results. In my SVL L0 normal, I get a smaller number of support vectors. Not the same. You from your finger, the support vector seems the same, almost like 15.
Yeah, I could mention there that I ran it a couple of times, and sometimes I like the final one, the one I have in my report, the L0 norm process had a couple of runs with smaller support vectors. But I think both are all right, because I ran it a couple of times and I got either this or what you're describing.
Yes, I think in the lecture 8, the professor Soiken said we use the L0 norm to do a further sparsity of our support vectors. So I believe maybe it tends to we should get a smaller number of support vectors here. I think it's from the theoretically views we should.
Actually, I don't remember like which part of the slide he mentioned about like this SVL0 norm. What do you know where did they mention this? Because I couldn't find any materials about this.
I remember in his gives some additional materials. I checked
Oh.
several days ago, but I forgot. Named the LS-SVM. It's just like a menu book.
Menu book.
There is
Is it on Toledo?
yes,
Yeah, I think
in
on Toledo there's a subfolder called additional materials.
Yes.
Okay. Check.
It
Supplement
didn't
material?
Yeah.
No.
This one.
This one?
LS-SVM. The name also LS-SVM. I checked.
Is this additional optional materials?
No. Let me check. I forgot.
So I think it's in the supplementary materials. I saw that. If you go down, yeah, here. So there's OTL SSVM. I'm not sure if this one.
Is it?
Maybe not. Doesn't seem to be. Never mind.
I feel like they posted about it in the announcements very recently.
Is it? Oh,
But I think in the exercise session.
oh. Okay.
Like, yeah. The other pages. Yeah, the third one.
Oh, okay. This one. Here's a picture for 142 about the. Oh, okay. Yeah, I don't know this. Very sparse. Wow.
Yes.
Very sparse.
It's still another material. Material, but I forgot which one. Is told about the.
Can you even download this? Oh, I even download this. Okay. Yeah, I haven't get the chance to read this actually. Okay, so then it's very sparse. Then it's more sparse than the another one, I guess. So this one is more sparse than this LF, like the fixed size LS-SVM, I guess. And then, yeah. And the Wisconsin breast cancer, I don't know what is the size of this data set. Let me quickly check this. What is this actually? Yeah, sometimes you go to 16.
I think if you run multiple times, for some runs you resulted in like smaller number of secure vectors. But I think it also depends on the nature of the data set. So maybe for this breast cancer data sets, 2 algorithms performs like similarly. It is still likely to happen.
Actually, I run multiple times and I get this result because I know that theoretically L0 should make more sparsity. So I also get the same results from you. So I run many times in order to get the right results.
But I don't think that you cannot just say, well, maybe you can do kind of like a statistic on it, because I think each run it's kind of like you have the equal, right? They are equal. I mean,
no, I don't think so, because you started from random like initial points, and those algorithms would converge to different subsets, I think. So it depends on like how lucky you are, and because I ran like 4 times and one time I got like So the mean is always the same, but for the SVL0 norm, you have an outlier that is lower. So yeah, that's what I got, but I think it really depends on the data set.
But I mean, what I mean is that I mean, you know, okay, beforehand, you know that okay, this L0 norm is gonna, you anticipate this to be more sparse, have more sparse probability, but you cannot just say, okay, I'm just gonna run. I'm just gonna pick the point, pick the result, which is like this one has less support vectors, and then I'm using that one, that will run for the result instead of like, but then you get many kinds of they're exactly the same, right? So
yeah, I think
Yeah.
what's good is that if you can show like those two results you got, and you explain to the professor what's the meaning behind it, that would be the best, I think. Because if you run multiple times, you can only get like two kinds of solutions. One is either they are the same or you get smaller. So you can show those results and you can explain it.
But okay, yeah, that's my point. I mean, you cannot. But here, so I think after, so let's if let's say now we are talking about after many rounds, like we want to have a, well, not so. I think after many rounds, so first of all, the error you get for FSSOMN, it should be lower than this one, right? Should be lower than this L0 L0 no. And for this one, well, yeah, the L0 no, sometimes it's equal, sometimes it's less, basically. And then for this one, like the computation time, actually, I mean, those kind of things actually don't really. I was just saying they are pretty much the same. I mean, they're not so different to me. I mean, just, and then the distribution is fine, I would say. But then, of course, yeah, you maybe can say maybe this one, like the L0 norm, is slightly better. I don't know if, well, I don't know if this is the one that I get from my report as well.
No, I got totally different results too. So for the time, my SVL0 norm is even higher. So it took longer time.
Yeah, but I mean they are close. I'm just saying they are close. But
Yeah,
in my case,
the mean,
they are really close.
The mean is
I
close.
just say,
yeah.
So I don't
I
really.
got they are close the computation time.
Yeah. So for that one, yeah, I don't think there's too much things needs to be explained there. I would say.
Yeah, indeed. I think there are just so many random factors playing.
Yeah. I think the interesting point that you're trying to explain here. Okay, first one, this test error things. Well, I think yeah. I mean, and then this one regarding to, of course, we need to talk about like the sparsity of those two. So, and then yeah, we just describe whatever you saw, like whatever you put in here, and then you just kind of like reasoning, like, because I also have I don't have like too much idea about how to explain in with this with some like reason. So I need to actually look it up, that paper. But this is basically what you get. Yeah, this we are just for this question. Let's just verify like the results, like result, and then if you, and then let's discuss the reasoning behind. Then let's do it. Let's leave everyone to try to explain this, I guess. Okay. So, any more on this? So I think yeah. So just let me know if you still have some question later on. Have this, but actually, yeah, the homework is actually quite straightforward now. So the first one is about using the kernel PCE to do some denoising with some digits. So again, you are trying to basically compare the difference between kernel linear and kernel, and with the same noise factors. And you need to check, okay, what is the sigma 2 is too big, what you got, what is small. So if you recall from the previous one, so your sigma 2 should be, how do you say? Let me check what I got. Okay. Sigma 2. Yeah, so basically I present those sigma, like the pictures with form pictures with different sigma factors. So I think it suggests like the default one from the script is 0.7. And then I try to, because they ask you to do a logarithmic scale, like you need to, so I just times 10 and then divide by 10. So I get like 0.07 and also with sigma factor 7 as well. So I just run this kernel PCA trying to restore it. And basically, so you kind of like just describe like with this. So you can see that's actually how do you the sigma 2 you cannot be like there is also kind of like optimal range for sigma factors as well. When you're trying to denoise it. And this one, the first one is between linear and kernel PCA, so you can see it very clearly. So I just compare those two. So you actually, if you increase your number of the components, it's actually the linear one is actually getting worse results. And this one, if you keep increasing, the quality of the reconstructed images is actually getting more clear than if you use lower number of the components. And what else? In order to investigate this, change. Yeah, so this is one. Yeah, you just need to. I think you just need to answer like there's definitely a good like optimal range for the sigma 2 in order to get the best dosing result. And here, then you're trying to investigate the reconstruction algorithm errors. You on those two, validation sets. So basically you need to implement like the strategy which you described before with the exercise in the kernel PCA. And so I basically what I did, I just so I was trying to first I need to fix the sigma, and then I was trying to calculate the values that I get from using different like the reconstruction arrows, which is from by using different number of the components, and I get something like this. So this is the one on the top part. So the plot on the top is actually the on the test 1, and the one on the bottom is on the test 2. So I was trying to, and so this is general, like you might get some different results, but the point is like, okay, you use this and then you figure out, okay, this is like basically you're trying to implement what you propose the strategy to actually tuning those parameters, and then you basically just trying to get the result of it. Okay. So comments on this exercises, questions?
I do have a question for this. So, if you look at the script, I noticed that they trained the SVM model using the clear digits, which seems to be strange in my point of view, because in the first exercise, which is also a denoising example, well, we just use like with noise data to train the SVM model. and use some of the dominant eigenvectors to denoise. But here you already trained the model with clear digits, and I don't know whether it's good. Here it seems strange to me.
Yeah, that's true. I mean, yeah. So you see here they are adding noise, but actually xn, what is x with this xn is using? Let me check.
It's only used to denoise, so not in the training phase.
Not in the training phase. That's true. Because I think in this one they are using just one. There's a function, like we use like this this RBF, you know, like pre-images RBF. Is this one?
Yeah.
And they put the train sigma 2 UD, which is like the UD is like the eigenvalues vectors, I think.
Yeah, I think so.
And then you just put the X train X test. So this one is actually the individual image, like the matrix of the individual images, and they just put something like this. So I'm not sure why they are. So that's why that's kind of strange, I would say.
Yeah, I don't know either. So I just want to confirm, like in theory, whether we should use like here or no noise data to train the model, or use like the
Yeah, but let me check. So which one is so this is the first this one, right?
yeah, indeed.
So you get a number of data points, MB, and then you have the sigma 2. And then here it's already yin and yang.
Sample yin and sample yang.
But the yin yang is like the pure data, right? This is one.
Yeah, but they don't use the pure data to train the model. So they used the sample yin and samples yang.
Okay, so this one is adding this one is like the one you add this kind of like a noise, right?
Random noise.
This is sample, and this is like not the random, right? This is just something like the ideal, like non-noise,
the function,
noise free. And then where's the function for the training? This denoise KPA, and they use sample yin and yang.
No, it's above. It's still above, because here
it's here
calculate the
so, okay.
You say it uses samples in samples yang to calculate the eigen values and the eigenvectors.
Yeah, that's true. Though. I mean, that's kind of a question mark here. Yeah, but yeah, I think maybe I think this one we need to probably also kind of like send a mail to TA, because this is something really strange. Where is it? So in the exercise, what happened? Why using this data to use for the training? Okay. So yeah. So if others also is there anyone want to comment on this? If not, we're gonna move on to the next question. Hello.
Yeah, we can move ahead, I think.
Yeah.
I'm not sure if that's what the question is asking, because it's if you can train your data with data without noise, and if it will work to denoise, but maybe it's better just to ask the TA.
Yeah, I agree. Yeah. Okay. So so now let's come to the homework of the fixed size LS-SVM, and we basically need to run the script again. When like in the beginning we run with Wisconsin and then dataset, and here we need to run both too. Okay. On the Shuttle and California. So first, you need to kind of like for the first one, you need to explore and then visualize the data sets, like how many data points, how many meaning of the attributes, how many classes. So this is just something that you can do just by using this link, I guess. So it's like so it has 9 attributes. So you got like 8 for as you got 8 as the how do you say as the, let me check what I write. This is something just tribal. So we have, so you have 8 attribute. Wait, this is, wait, check. Oh, check the code out also, just to be sure.
I have one question on the data set, but maybe on the previous part. How did you know that we had to use Wisconsin breast data on 1.3?
Well, it's it says that. It asks you, right? I mean, wait. So you are talking about the first one, right? So yeah, it's here says use Wisconsin for this exercise.
Yeah, I have a different version of that. I'll look into that. Thanks.
Again, maybe,
Yeah, for me,
but
this question asks me to run the same one, the shuttle.
oh, okay.
I think they updated this file like 2 days ago.
Really?
Yeah,
Maybe
you remember they put an announcement saying there was something wrong with the code and they uploaded new materials.
yeah, but that's, I thought they just like did the code, right? Like I mean, because for that to shadow, you need to actually how do you say, you need to put the label like to 1 and the -1, right? That's what I heard, but I don't know, like there's even some changes in the exercise.
Yeah, but I think yours is right, so I will adjust mine.
Well, let me
It
check.
makes more sense. Yeah.
But I don't know. I mean, we need to, well, we need to use the updated documents, right? Let me check that just to check this assignment exercise 3. Exercise 3. So, well, okay. Let me check. Oh, I think they just deleted this, huh? Isn't it?
It's weird.
What the? Okay.
Yeah, that's what I asked, but it makes sense that it is the breast data. But
yeah, for me it makes sense too.
Yeah.
Yeah, because I download this document like in the beginning of the semester, so it's like the even like, so I don't know, but maybe yeah, we need to kind of like because I think no one even asks this during the exercise session, like with TA, you know, like I don't know.
I think this is so trivial that nobody really realizes there's a difference.
Okay, that's
Because I
interesting.
I didn't even notice it until you showed your like risk and cancer dataset to us. So,
But what did you guys use then? Like, did you just
Because
use Wisconsin?
no, because by default the dataset used was the Shuttle one, and here it says just run the script. So I didn't change anything, and the results are just
Oh,
the Shuttle.
okay. Okay, one more thing is to check with TA for this. Okay, this is question 1.3. So let me check. So 1.3, fixed size, this one, which data set to use. Okay. All right. So that's a good observation. All right. So here, yeah. So I think in the first question, I don't think that needs too much explanation. You kind of found everything online using this, and then you visualize, explain this result. So again, so in this one, that's just I think yeah, it's just to try just verify what everybody is getting. So we're not gonna explain too much why do you getting this, because I don't think there's some like a very clear answer to that right now. So let me check what I get for the shuttle. So yeah, so I try to visualize this using this this kind of plot using the TSNE kind of like plotting. So which is I used before in the exercise 1 as well. So you get this, I get this kind of a plot. So again, this one seems to be like the error 1 norm has a smaller, like a lower test error. And the supporter vector I get, yeah, it's again pretty much the same one. And this one, it's again like the computation speed. I think yeah, they're just close. I mean, sometimes maybe you get one higher than another, but they are very close.
I do have a question on the arrow. Do you guys know what's the meaning of the arrow? Is this something like the MSE, or it's the like accuracy, or how many data points were dismissed, classified, and divided by the total number of points? I'm not sure about that.
Well, yeah, I mean here, I think because this one is a classification problem, so I think it's like something like a misclassification rate or something, I guess. I mean, from what we used before.
I have a question. Because the home data is about 58,000. So I think it's really computational expensive. So I really actually I just run test about 1,050 points. I want to know, is it okay?
But that's also my question. I asked it in the group.
Yeah.
By default, they only use 700 data points. So those data equals to data 1 to 700. And I'm not still sure how they got this number. Yeah.
I think it's something. I think it's something that they want you to compare, because for this shuttle, so if you didn't change anything. So someone wants to speak about this or what?
Yes, I have a question. How did you increase the performance of this model. I get like an error of 17% or something like that. I think you heard me before testing the microphone, so sorry about that.
So what's your question again?
Yes, how do you, like with all of the parameters, mainly the K and the window, how do you improve the performance of this model? How do you cross-validate with this LS-SVM, or just improve the parameters?
Well, parameters actually, I don't think that is asking the.
No, I didn't even change them.
Yeah, it's just ask you how many, like you just need to run the script and I think you just obtain the result.
I know that's for 2.2.2. Maybe.
Yeah.
You mean California dataset?
Because for those two, like Shuttle and California, they are exactly the same question, right? There's nothing that.
So do we really need to change or try to improve the performance of this, or do we just leave the parameters?
Well,
there?
I think we can just leave it there. There's no such like any indication that asks you to optimize the performance.
Okay, yeah, I guess so.
Otherwise, yeah.
Yeah, and the documentation's not that straightforward.
All right. Okay, I think that's clear. That's. I think we're clear about that. So another one. So like, just get back to why you. So like you guys said. So actually, the Shuttle for this data set is actually more than just 700. So but I think when I was. So it's choosing this, right? It's just choosing, if you default one, it's 700. But I think it's trying to, I think what they were trying to let you compare is actually, because if you go with a California data set, then you have a lot. Like you get like 20, let me check, what is the data set? So you get, so for California, you get this about 20,000 and 6. So I think what they are trying to do here is trying to compare, like if you have a very small, if you have the difference between you know, like moderated data set size and this large data set size. I think they are trying to this basically for those two data sets. One is like a small data set, and then one is large data set, and they want you to compare the difference between those two. Maybe. I'm just
do you mean we have to run all this data?
No, I mean, I don't. I think you can just leave the default one just for the Shuttle. For the Shuttle one, the data set you just leave it like 700. You just leave it as it is, and because and then the one with California, they are like 2064 though. So you can just also, I think they are trying to, you know, get the result from large scale and also the small scale problem, and then trying to ask you, and you kind of trying to give you an idea like which kind of like process is getting better, whether it's FS Fixed-size LS-SVM or this kind of like SV01 norm. So
I don't
this
know
is just my.
If I didn't use the home data state, I just use subset. Maybe I cannot get right conclusion. So it's my biggest worry.
But they didn't ask you to. I mean, there's no announcement to ask you to change that data set, right? Change the number of data sets in the Shuttle, right?
Yes, in both the Shuttle data set and the California data set, I only use 1050 because just yesterday I'm trying to run all this data. I find my computer is very hot, so I stopped it. Yeah, it's
But does it, why do you think you should run with that kind of data set instead of like 700? I mean, you can try that. You can try anything, but
I just think 700 is limited. Maybe maybe original problems is just about a large scale data set. Maybe I can try as large as possible.
Well, I
Yeah,
tried
just-
to use the whole data set for the first question, but turns out my computer cannot do that. So yeah, I just keep it
So
to
maybe-
be 700.
so maybe you shouldn't do that.
Yeah, but that's weird because this is large scale
Yes,
SVM, right? It's
Yeah.
supposed to run a really large data set, and the algorithm would pick some small subset for you. But it turns out to be not the case, and that's why I'm asking this question.
I do
Yeah,
have
so-
on that because I could run the 50,000 records. Like I read the whole file and ran it, but to prevent it to take such a long time, I just ran one of the two processes.
Hours?
Yeah,
Oh.
so I only did fixed-size LS-SVM and didn't do the L0 norm.
Okay.
And how long does the fixed size take?
I do have the image.
Like
let me-
approximately less than 1 hour or something.
I think it's more than 2 hours.
I'm not sure. It didn't take that long. It took 110 seconds each iteration, and it did 10 iterations. So and I don't think my computer is that good like for this. But yeah, that's what I can say. It might be a better approach to just leave the data at 700 because it's not specific about running
Yeah,
the whole.
indeed. Yeah, I
Um,
get that.
Yeah, I was more worried about I did run it, but I couldn't, even if I have the error and the cost, I don't know what the solution is because the function, it does not give back what are the parameters that the solution gave. It tells me I used 40 support vectors. Yeah, but what were the 40 support vectors and what were the parameters that optimize and that's what I couldn't get, but I guess that the question is not asking for that. Yeah.
So how long did you actually the whole process that you need to run like with this? If you just run with one process?
Maybe 6 minutes, 7 minutes.
I'm not so sure about the theory, but is there any difference between the fixed size and the L0 norm in respect to the data size? Because I know fixed size is meant to deal with large data sets, right? I'm not so sure about the SVL0 norm.
Yeah, I didn't run L0, so maybe that's a good hypothesis.
Because the Shuttle data set is an unbalanced data set. So I think if I choose only 1015 data, maybe I choose it's contains some probability because it is unbalanced data. So maybe I get a good result or bad result. It's random.
Yeah, but I think the people who uploaded this dataset already randomized all those datasets. So
yeah, if you can see my result here, so the one with the red one is -1, so the 20%, and the one with this kind of like blue is like the major one, like the with 80%. So I think this is quite, I don't know, maybe I didn't count like how many they have, but I think it's quite approximate, I would say. It's not that so unbalanced. It's kind of like to its nature, I would say.
Well, my guess about the data size restricted to 700 is because you have some like the Renyi entropy criteria to select the small subset, right? When you're like the whole data set is large, that might take really long time. So that's why maybe they just restrict that to be 700.
I just think 700 is a random number, so I changed it.
Okay. But here, I mean, normally, well, this kind of thing, I mean, if they don't tell you to change it, normally it's not suggested you can change it. I was,
Yeah, indeed.
But,
so I didn't change it.
Okay.
in the end.
Okay. Maybe
we
I
can
it's meant
ask
for
the
the-
TA.
But
think it's
even
meant
if
for
you
the
change
first
it, I wouldn't say there would be much difference even if you change it.
Yes, I believe. I also think the 700 is a random. It's I don't know. Maybe just like you think it's some spatial number here, spatial setting.
All right.
I don't know about anyone else, but I'm getting an error near 20%, which is pretty much not pretty that good. Just with the raw script.
Error?
Yeah, I mean the precision, 1 minus precision.
You are talking about the California or?
No, the shuttle data set.
You are getting errors when you're running a script.
No, I mean the misclassification.
Oh, okay. Let me check what I get
Which
here.
is quite large considering that 80% are from one category.
Okay. This is what I get here. And let me check what I get in the report I put it in. Yeah. So basically for this one, so for the test error, you will get like this one is higher, like you will get this LFS higher error on this LS-SVM. Just to be sure, yeah. So this is also the same. This is just different scale.
I got
so
the opposite actually.
Really?
So for me, yeah, the L0 norm had higher error.
Anyone else is the opposite? Or
I also guess the error estimate is higher in SVL0. No.
maybe, yeah, just wrong. Did you get this kind of thing every time or just one time? Maybe you should do multiple run on this just to be sure.
Yeah,
Because this is something I didn't change. I mean, I just run the code.
Yeah, I didn't change, but I got the opposite. Because for like in principle, it's very sparse approximation. So yeah, you would expect the results to be poor, I guess.
Yes. Did you run all the data set?
No,
Or
no, only 700.
Only 700. Yeah.
Anyone else is getting the opposite? Because now we have 2 versus 1. Okay, somebody on the chat. Well, I cannot read some script files. They come in some kind of encrypted. What? Yeah, so that's why Nicolas, I don't know. Yeah, that is something purely technical about the script.
maybe I'll try with the different the training and test data sets.
Yeah. Yeah, if everything doesn't work, just reinstall everything, download the new script, whatever.
Yeah.
Okay.
Hopefully.
All right. So, yeah. So like I said, so normally, so I would say, yeah, this then for this data set, the L01 is getting smaller test error, and then again the support vector, they're pretty much the same, and also the computation speed, they're pretty much the same. Okay, so let's move on to the next one. So next one is the California data set. So and here, so you need to explore and visualize the data set, how many data points, blah blah blah. And you're trying to, so here you need to actually explain the meaning of each attribute. So for like, but actually for the Shuttle database, Shuttle data set, I think, yeah, we only know kind of like, like, I don't know what is the other, like the full kind of like the meaning of each attribute actually. I know like two of them, they describe it, like one is a class and another one is like time or something. And then I don't, for the rest, I don't know what they mean, like the data. I don't know if anyone else finds some information about that.
Yeah, if you search for the California housing datasets, there.
No, I
you
mean
can
talking
find-
about the Shuttle dataset.
Okay.
Did you anyone find anything about the full description of the Shuttle or for the Shuttle dataset attributes?
No,
This is just something trivial, huh? I mean, just make sure. Just yeah, if not, we just continue. So like I said, if you just Google what is a California dataset, you will get this kind of explanation for each attribute. So like, because this is basically kind of like housing price prediction data. And so I was trying to, so you need to visualize. So because this is a function, this is not a classification problem anymore. So I just basically plot the histogram for this kind of like for each kind of attribute. So there's also other ways to do it. So one of the from the TA, one of the method is to do something looks like this. Change this. So it's a kind of like they're doing this kind of like plot, box plot or something. So you can also do it here, but it's your choice basically. How do you want to visualize this? All right. So next, so again, so let's just verify the running of that script. So here, let me check. So now you have much more. Now I think you can say this is a large data problem, large problem right now. And here you can see that like the LS-SVM tends to have a smaller test error than this one. And also I get something from this, but maybe I should just quickly run it again just to verify this again. Just check. Just just quickly verify whether it is consistent or not. Yeah, taking a while. No, this is going to take some time, isn't it?
Yeah.
So before we get to this run, so do we have a different result regarding to the test error? So I would suspect that this fixed size, this one should have lower errors.
Yeah.
Is
pretty
anyone?
similar.
Okay. And how about this support vectors? Did you get something like this or something different? Check.
My results didn't get this sparsity. The support vector numbers is the same. So maybe something is related about my data point choice.
Data point choice?
I mean, I just choose 1015 data points.
Oh, so
Yeah.
you didn't choose all, like you.
Yeah.
Okay.
Yes. In both California and the Shuttle dataset, I choose 1015.
Okay. Yeah. So, but then there's no meaning of comparison because we are using different data sets.
Yeah.
Okay,
you
so
run
I
all the
get
data?
again. So yeah, so actually, yeah, you also. So this is my another run. So again, the arrow for LS-SVM is better, is less, and now I get to the same number of the support vector again, and the
By the way,
computers.
do you know what's the meaning of that red cross? So
red cross is the outlier, basically.
yeah, but if you look at number of supporter vectors, I don't think there is a meaning for any outliers. You get the exact amount of supporter vectors, right? Why there
No,
is an
in
outlier?
here it's like a mean, like this is like a mean or something, like this red line. But here, so you basically have a distribution of this of your support. Let me just tell. So this one, okay, the support vector is actually the parameter, like the return of this function, right? So it's the return of this s. So basically, you return the support vector numbers for those two processes. So this, if you open it, you can see that, okay, they are both, so this one, first one is the fixed size SVM, and this one is the L0 norm. So you see that, okay, yeah, so you actually get 10, you get 10 kind of like results
Okay,
for
so
each.
yeah, so there are 10 trials. Okay, I didn't realize that.
Yeah. Yeah, because like those kind of box plot is basically it's kind of like a statistic like analyze basically. So if you for that more you can check what in the MATLAB what this kind of like a like box plot is doing. So basically you get like this is one of the outlier, I guess. So you consider this as an outlier. But it's actually one of your results basically. Okay. So I think, yeah, so for this one, so in general for the California, so this test arrow should be lower. And this one, I don't know, I'm not sure about this, but in principle, then it's, of course, again, this one has more sparsity. So maybe you will sometimes observe this one has lower support vectors. And then computation speed is it's the same. It's not, it's close basically. All right. Okay, so I think for me, I think let's conclude this sessions. And anything more question that that you want to ask, you can.
I still have a question regarding the first exercise. So about the ROC curve, I remember last time someone got a flat ROC curve, and I do get that. And I'm wondering if there's a solution.
Flat? What do you mean?
So all one.
Yeah, it was me who asked, and I did get something different. There's two options. Either in your code, you're modifying your Y test, because for some reason in the code they put
-1.
in the first exercise session, and it was on the ROCs.
Okay.
Because some of the
Can you-
ROC curves.
Yeah, question 11, I think. So in question 11 about ROC curve, I think.
Yeah, some ROCs were just one, but if I'm not sure if this is something general or if it's only you, maybe just give me a call in I'll put something in the SVM group in WhatsApp, so you can give me a call.
Are you talking about this question? Or
no? So before question 10, I think it asks you to run the script and it gives you an ROC curve, I think.
okay. But it's something on question 1, right? Like exercise 1, sorry.
Yes. Yeah.
Yes.
Well, you mean like you are getting a flat, like a ROC curve, or what?
Yeah, if you run it in some way, you get like a perfect classifier. Like
Yeah,
that.
here. Yeah, you also
Yeah,
get
yeah.
that.
Yeah, I also get that. This one, right? So which one?
Yeah.
Question 12.
Yeah, exactly this one. So it's flat.
Yeah. So yeah. So basically, well, yeah, it means that you get a perfect classifier. Huh? I mean,
But in principle, if you have a really low threshold, then you shouldn't get that high, right? So I'm asking why. Is there any problem?
but what is the context of this? You are trying to check.
It was a question where we were automatically tuning the sigma and gamma values to train an SVM model and then make an ROC curve of it.
This one, right? This one. So this one, and then automatic detuning, right? Oh, ROC. So is this one, right? So we can generate this ROC curve for this. Use the tune, gamma, and sigma 2.
Yes, that's one.
But well, I don't see any part that you need to set up some threshold.
No, I mean for the ROC curve, it sets different thresholds and right. So I don't think getting a flat line is correct, because normally if the threshold is 0, you shouldn't get everything nicely classified.
Well, it's 0, and it's like you are getting, how do you say? So if your threshold is 1, but this is so this is just a representation of the perfect like classifier, right? I mean, it's just like you just classify every data correctly.
Yeah, I got the same thing, so I thought it was just correct.
Yeah, I mean, if you interpret this, so you know that, okay, if you are like, it's a diagonal line, then it's a random generators. And then if you, the normal, in some cases, you get some curve like this. And if you're doing like this, it means you cover all the area, then it's like, meaning you can do all the, like, the classification correctly, right?
Yeah, but intuitively, you shouldn't get this such ideal case in real life, right? Because
Well, but
the RC curve will change the.
Does this data is from real life? I mean, because I think when I was running this, actually the data is like quite small, right? I don't know how many data points they have. They are just like hundreds or 10. I don't know. They're not so. I would say they are not so realistic. This iris map, right?
Yeah, because I remember last time you guys discussed this. So yeah, I got the same as you. So I'm not sure if there's anything wrong though.
Well, is there anyone getting other than this, like this kind of results?
I got something different, but I changed the code I used. I'll put it in the chat because the function that they gave us in the wasn't giving me while latent that worked, so I used that and I got 0.95 in area, which is almost perfect. But yeah, you're right, because in this data there's just 20 items, I think, in the test. So either you get 5% wrong or you get it all right. So it's I wouldn't worry too much as long as there are other, because I think in exercise 2 we also have to do some ROC curves. So if there you get some shape, that makes more sense.
Yeah, so this is the code. I mean, you're just doing some automatic tuning, and then you just use these things to kind of like calculate whatever, like to calculate this Y length, and then you use this. Yep.
Yeah, so the only thing I did different was use latent LS-SVM to get the Y latent variable instead of that, because
Okay.
I'm not sure of the output that gives.
Okay. So you just try a different style of code, and then you are able. I don't know who else is. If you just using this, huh? If you are just using this, I mean, I don't know. Someone get this others result or not. But anyway, I mean, if you look at this part here, I mean, it's just like, I mean, like you said, just 20 points, and they are quite actually distinguished. And then, yeah, it's possible that maybe this is so ideal. I don't know. I forgot, but this is like the data used for training the results, right? I think the test data, because you are performing this on the test data, and the actual test data is even far less than this. And I don't know how they distribute it, but if they fit this model perfectly, then you will get something like this.
Yeah, maybe if everyone gets the same plot, this should be okay.
Yep. Okay. Anything else? Okay, I think let me just stop the recording just for because now we are just not discussing about the how do you say?